Okay, we're going to revisit a problem that we actually ended on in the last class, and that's taking this graph, which was square root of x, from, say, 1 to 5. I think in class we did from 1 to 9. And we're going to revolve it about the y-axis so that the shape we actually get looks something like this. Some students said it looks like a stadium or like some sort of bowl. The way we did it was we sliced it up using washers, and it involved two integrals. But this time we're actually going to use the idea of what's called shells. So let me show you these shells, and then we'll take a look at one shell and how to integrate it. So if you kind of think of shells as layers, and all we're going to do is peel the layers away, calculate the volume of one layer, and then add them all up using integration. Okay, so let me show you one shell. So here's one shell. Let me make it, in fact, let me make it really thin so you can kind of see. It's a very thin shell, and let me lift it out so you can kind of see it's sort of a very hollow cylinder, and we're just going to add up all these hollow cylinders, and that should get us the volume of the shape. So we're going to be talking about volumes by shell. I'm going to go kind of fast, so if you need to rewind or pause the podcast, that's fine. So we're going to revolve this region around the y-axis. So roughly speaking, you kind of get this reflected region over here. It looks something like this. And just to give it a little bit of definition, we'll add some roundness to the shape. Again, this is not very necessary, but it just kind of gives you an idea of what we're looking at in 3D space. So here's how we're going to approach our shells. The first thing you're going to do is you're going to pick a random spot somewhere in the region. I'm just going to pick this spot right there. And this distance we are going to call little r. Okay. Once you pick the spot, then you're going to draw a height, top minus bottom like we do in class, and that's going to be the height of your shell. And just to give you an idea of what the shell looks like, I'll draw it completely. So here's your shell. Okay. Let's take that shell and let's move it elsewhere. Okay, so here it is. Very, very thin cylinder. The thickness of the cylinder is going to be dx. Very, very thin. Okay, and you can see the thickness is right here, dx. Okay, now let's say I slice the cylinder right down the middle, and I open it up. Well, what shape would you see? You would actually see a rectangle. So we can find the volume of this rectangle pretty easily because we know the thickness of this rectangle is dx. We also know that the height of this rectangle we'll call h. And the base of this rectangle actually is just the circumference of this circle, which is 2 pi r. So the volume of this shape is going to be length times width times depth. So you can think of it as 2 pi r times h times dx. That's going to give you the volume of the shape. And in order to get the volume of the whole region, we're just going to integrate this. Okay, so now here's where it's a little bit tricky, determining r and h. H is usually easy, and you can see here, if we do top minus bottom, h is just the graph. So it's 2 square root of x minus 0, technically, but our h is just going to be 2 square root of x. Students have a lot of trouble figuring out what r is. Since r was a random spot, it's really from this point to the axis. This random spot is really just an x value. So r, right minus left, is just x minus the left side of that is just 0. Okay? So we'll get a little bit more practice, and hopefully it'll make more sense. So in this situation, I'll pull out the 2 pi. Integral r, we just said was x. H, we said is 2 square root of x. And then dx gives it some thickness. So now what in the world are our bounds? Well, you have to think about where the first shell is. The first shell is actually here. And then the last shell is actually here. Because you're moving in dx, you're integrating the shells as they go outwards in this direction. So the first shell is at x equal to 1. The last shell is at x equal to 4. So your bound should be from 1 to 4. Okay, let's take a look at the same shape, but this time we're going to revolve it about x is equal to negative 3. So it's actually going to get revolved around a line that's a little further out than when we had it last time. So when I try to draw the reflection of that shape, it's a little bit further out. So we'll do the same thing. I'm going to pick a random spot. We'll just call that spot. And then from there, I'm going to create my height at that random spot, which is translated over here. And I'll try to draw the shell just to give you a visual. So there's the cylindrical shell. So again, we need to find r. So r is always from the axis to our random spot. Now remember, our random spot was x. Okay, so r here, if you do right minus left, should be x on the right minus on the left is negative 3. Our h is this line, which is top minus bottom. So on top, it's going to be 2 rad x. On the bottom, it's minus 0. So to get the volume of this shape, again, it's just going to be a rectangle where the base of the rectangle is 2 pi r. The height is h. Give it some thickness dx. Integrate, and that should give you your volume. Now think of the bounds again. Our left, because it's dx, our leftmost shell is actually here. Okay? And our rightmost shell is going to be here. So the bounds again are 1 to 4. Okay, let's take a look at a situation where our graph is actually revolved around the x-axis. The graph of this function, it's not really a function in x, but is a function in y, is actually an upside down parabola that looks like this. Okay? And since we're only going to the y-axis, the region in question is this region, and we're spinning about the x-axis. So if I reflect it, it's over here. And let's draw our shell. So now our shell's thickness is actually going to be dy. So I'm going to pick a random spot. That's going to be my r. I'm going to draw height this direction this time. Call that h. I'll kind of translate the shell here. So here is our shell. Okay, so now we just have to determine r and h. Because r was starting from a random spot to the y-axis, it's just y, which is this spot here, to the axis, which is 0, so y minus 0. H, because of the way I drew the line here, it's a right minus left. So to the right of that is the function negative y times y minus 2, and to the left of that is 0. So there's my r and my h. Notice here that the thickness of my shell is now dy, so that's why I know to write everything in terms of y. So my setup, the volume of my shell is 2 pi r times h. Integrate to add them all up. So let's look at the bounds again. Now we're going in the y direction. So the bottommost shell, instead of going left to right, we're going to go bottom to top. The bottommost shell is down here, and the topmost shell is over here. So the bound should go from 0 to, and you can actually show that that's 2, 0 to 2. Let's do a little more practice using some graphs that are already pre-printed for us. So we're going to spin this graph, which is negative x squared plus 2x from 0 to 2, about certain axes. Just so we don't lose sight of what we're doing, here's that graph, and we're going to spin it about, let's say in this situation, the y-axis. So we're going to get this shape, and once we get this shape, we're going to just create some shells. Again, let me make the shell pretty thin and pull it out for you to see. So there's what the shell will look like. Okay? So let's assume for this particular situation, I want to revolve it around the line y equal to, let's just assume that's negative 2, even though I missed it. Okay, so what we're going to do, we're going to pick a random spot in the interval, and that's going to give me my h. Okay, and then from the axis to that random spot, it's going to give me my r. And if you want to see the shell, I'll kind of draw the shell a little bit. Okay, so in this situation, h would be just that graph, which is negative x squared plus 2x. And r, in this case, random spot is x to the axis. So it's x minus negative 2, right minus left. If we go on to the next graph, let's say I put my axis instead at x is equal to 3. So I'm going to pick a random spot in the interval. I'm going to use that spot to draw a height, and my radius is going to be from the axis to my random spot. Okay? And then again, here, let me kind of sketch the shell so you can kind of see it. So in this situation, again, my h is just negative x squared plus 2x minus 0. And my r is right minus left. Right minus left. So on the right, I have x equals 3. On the left, I have the random spot, which is x. Right minus left. Let's go on to this function. So in this situation, I actually have two curves. One is sine and one is cosine, and I'm only going from this interval. So let's say I randomly say I want to spin it about x is equal to 1/2. Okay, so same thing. I'm going to pick a random spot in the interval, and I'm going to draw a height from that spot. Okay, and then my radius is going to go from my axis to that random spot. That's going to be r. And again, if you really want to see the shell, it looks something like this. So if you look at h now, it's top minus bottom. The graph on top is sine, minus the graph on the bottom is cosine. R is right minus left. So to the right is my random spot, x. To the left is my axis, 1/2. So that gives you h and r. You just plug it into the formula we established earlier. Similarly here, if let's say I wanted to spin it about x is equal to 2, pick a random spot in the interval. At that spot, draw a height. There's my height. H. R is from the axis to that random spot. So there's my R. And then here's your cylindrical shell. So H is top minus bottom. On top is sine. Minus on the bottom is cosine. Okay, my R is right minus left. To the right is 2. And to the left is my random spot, x. Okay, plug it in the formula, just because we haven't done one with the bounds, so we would integrate 2 pi r times h dx. The bounds, the leftmost shell is over here, the rightmost shell is over there, so your bound should just be pi over 4 to pi over 2. Let's look at just a couple situations in the y direction. Let's say we're given this graph, and I want to revolve around the line y equal to -1. So now we know we're actually going in the up and down direction. So I have to pick a random spot and use that to draw my height. So my height is now going sideways. There's my height. And the radius r is still the same from the random point to the axis. So that's my r. Here's my shell. Because the thickness of my shell is dy, that means I better change everything into y. So if rewriting this, originally it was y equals 1 over x squared. Move the x squared over, 1 over y, square root. So square root of 1 over y. Technically plus or minus, but without too much thinking you could show that this is the positive case. Okay, so now h is right minus left. So in RH, the one on the right is this line, which is 2. Graph on the left is this graph, which is minus square root of 1 over y. R, again, is a random spot to the axis, so it's top minus bottom. So on top is y, because that's a random spot. And on the bottom is minus -1. So there's your h and there's your r. Similarly, if I had chosen, say, an interval up here, let's say y equals 2.5. Okay, pick a random spot in the interval. Use that to draw your h. R is from the axis to that random spot. Okay, so h in this case is right minus left, so on my right is 2, and on my left is the graph, square root of 1 minus y. Okay, r is a little trickier. It's top minus bottom, so on top is my line 2.5, minus, and on the bottom is my random spot y. Okay, so what are the bounds though? So I got integral 2 pi r h dy. So since it's dy, I got to go from bottom top. So I have to integrate from here all the way up to here. Okay, so I have to figure out where those points lie by plugging in the x values into the equation. So when x is 2, y is 1 over 2 squared, which is 1/4. And when x is 1/2, I think this picture is a little bit off. It turns out that y should be closer to 4. So for whatever reason, the picture doesn't quite match the graph.